And
Cool.
go ahead.
Yeah, thanks so much for having me. People should feel free to like interrupt me in the middle. My talk is like almost definitely too long, which means that it's okay if you're not like it's not going to be your fault if I don't get through all of it. This is my first attempt at giving a talk like this, and so I'm trying to like both. I'm going to try to explain in the first half of the talk what is the actual result that we proved and why it's interesting, and then in the second half of the talk I sort of want to go through sort of a process as kind of like a case study of the way we were using AI tools, but as a result of gluing these two talks together, again probably too long, but um, yeah, we can talk more in the Q&A after. So, okay, and I'm going to talk about sort of a collaboration, sort of resulting in two papers with my excellent students Natalie, Joyao, and George. So to start, I want to get you into the spirit of why you might even be interested in thinking about calibration, and to start at the very beginning. I'd like you to reflect on what probabilities are and how we can make sense of them. So, like in a probability 101 class, you might get a question like, what is the probability that if I flip a fair coin 16 times, I get exactly 9 heads? And it's a pretty simple question. There's various ways you could go about answering it. For example, we've got a very clean mathematical model that happens to map well onto reality. You can model a coin flip as a Bernoulli random variable, and you can just, in that model, compute the answer to this question in closed form. And the reason this is a good model is because like you can also just like conduct the experiment. This is a repeatable experiment. You can flip the coin many times, you can count things, you can take averages. And like the mathematical model is a good one because the results you get from the mathematical model map very well onto the results you get if you conduct the experiment. It's just kind of like a shorthand for computing the experiment. Okay, so this is sort of like a friendly kind of probability. But this is, I think, the unusual case. Most probabilities that we talk about are not like this. So, for example, you can ask a question like, what is the probability that JD Vance will win the 2028 presidential election? And like you can go to Polymarket and get actual numbers on this. You can like bet on it if you want. At the time that I took this screenshot, sort of the market like believed there was a 20.7% chance. But like, what does that mean? And so like you can sort of get tangled up in all sorts of philosophical considerations if you like dive down this path. Like if you posit some probabilistic model of the universe with like quantum effects or something, then maybe it's at least philosophically coherent to believe that an event like this has some. If I reran the universe from the beginning to the end over and over and over again, 20% of the time, JD Vance would win the 2028 presidential election. But like it's not actually an event that I can repeat, so I don't have the ability to compute this probability empirically to estimate it. And certainly we don't have any mathematical models that we believe, map even remotely well enough onto reality to compute this thing. And so, this kind of probability, like in some sense, is really out of reach. And I'd argue that like most probabilities that we try to estimate are like this because, y- you know, like feature space, the set of things we observe is generally so rich that nothing is really a repeatable event, right? If I'm trying to do something mundane like, price life insurance, and I'm trying to just estimate the probability that some particular like customer Alice will die in the next 24 months. Um, like I've never before had a customer exactly like Alice. I can try to group her in various ways with, other customers and try to like estimate things, but like Alice is either has but one life to live. So most things I'd argue are more like this. Okay. So like we can't really hope to like learn true probabilities in general, whatever those are. We can't even check if we've done it. And so it's sensible to ask like what are the properties of true probabilities that make them useful? Like, presumably we wanted true probabilities in various contexts because it let us do things downstream, make good decisions. For example, did we really need true probabilities, whatever those are, or were there, just some properties about them that were sufficient to be useful? And in general, we should ask, like, well, like if we can isolate what are the useful properties of probabilities, even though we can't learn true probabilities, maybe we can learn those useful properties. Okay, so let me tell you about calibration, which is an extremely simple property, like kind of like a minimal thing you would ask for a probability to satisfy. Okay, so suppose you turn on like the weather channel, and the weather forecaster says, I think there's a 70% chance of rain tomorrow. Okay, and then you wait until tomorrow, and like guess what? It doesn't rain. So like how do you evaluate whether the weather forecaster like made a good forecast or not? Like it's totally unclear if she just made this one forecast because like things that have only a 30% chance of happening happen all the time. But fortunately, most weather forecasters aren't just kind of like weather forecasting dilettantes that make like one forecast. They're professional forecasters, and they develop a track record over time. They predict the chance of rain every day. And to the extent that you have like a forecaster with a track record, even though you can't really tell whether like they're forecasting correct probabilities, whatever that would mean, every day, you can at least like subject their track record to sort of statistical tests that are designed to falsify the premise that they're predicting real probabilities. You can check whether the transcript of forecasts has the properties that real probabilities would have. So for example, like if I zoom in on all of the days for which the forecaster predicted a 70% chance of rain, if these were real probabilities, it should have rained about 70% of the time. Right. Similarly, if I zoom in on all of the days for which they predicted a 20% chance of rain, if they were forecasting real probabilities, it should have rained roughly 20% of the time. Right. And this weather forecaster fails the test at the 20% level. Right. So think about calibration as kind of like a minimal statistical test. It can't establish that what you're predicting are real probabilities, but it at least has the potential to falsify it. Okay, so what does it mean? Well, suppose we've got some distribution on labeled examples. Let's say for now the labels are binary, like it rains or it doesn't. A calibrated forecaster, which maps features to predictions of like the probability of rain, is just a forecaster that is an unbiased estimate of the outcome, unbiased not just overall, but unbiased also conditional on the prediction itself. It's kind of like the self-referential consistency condition. You should be unbiased conditional on the prediction itself. Now, of course, you're not going to be exactly unbiased. Like suppose I predict that a coin flip has 50% chance of being heads, like I'm, like maybe on the distribution, I am exactly unbiased. But if I flip the coin 10 times, like it's not surprising if I get like 4 heads instead of 6, right? Or instead of 5, right? So like empirically, I will have some bias. And so we need to measure like approximate calibration error. And here's a standard way of doing it. If the forecasts are supposed to have 0 bias, conditional on the prediction, actually they'll probably for each prediction have some bias. We can measure the magnitude of that bias. And then we can just kind of measure like the average magnitude of the bias conditional on the prediction we make as averaged over sort of the predictions we make. Okay, and that's sort of a standard measure called expected calibration error. Now, why is calibration interesting? Like, why would we study calibration? Well, even though it's like this really simple thing, it already contains some of the properties that make probabilities useful. Okay, and in particular, like it provides a straightforward or trustworthy interface between predictions and decisions. And so here's like, there's many ways of quantifying it, but like, here's one sort of statement that's particularly nice. So suppose I've got like some model that has low calibration error. Well, why am I predicting, like the probability of rain? And, well, probably it's because there's some downstream decision maker who, needs to like take some action, like decide whether to bring an umbrella or not. And the thing I'm predicting is kind of decision relevant to them. Like if it's going to rain, they'd like to bring an umbrella. Um, so if the predictions have sort of low calibration error, then it turns out that simultaneously for every downstream decision maker, and these different downstream decision makers might have different actions available to them. They might have different utility functions. They care about different things. But it doesn't matter. I don't need to know what those are. For any downstream decision maker or for any utility function they might have, it turns out that if they're trying to figure out the optimal policy mapping my predictions to actions, if my predictions are calibrated, the optimal policy amongst all policies they could possibly choose is the one that just trusts that my predictions are correct and acts accordingly. Meaning they should solve an expectation maximization problem, maximize their expected utility under the distribution predicted by my prediction, right? They just trust the prediction and act accordingly. And calibration promises that's the best thing you could possibly do as a function of the prediction. Okay, like not so fast. Like we already noted that like calibration is already like a pretty simple condition. It just asks, right, you can throw away lots of information about the real instance and still be calibrated. It just asks the prediction be statistically unbiased, conditional on the prediction value itself. So for example, if I want to make that conditioning event like conditional on the prediction value itself kind of vacuous, I could just have a constant predictor, right? My predictor doesn't discriminate at all. It predicts the same thing for every feature vector it sees. And so long as the thing it predicts is just the label expectation, well, then I'm calibrated, but like, I'm not super useful. That's like a weather forecaster who predicts a 30% chance of rain every single day because, like on average in Seattle or something, like it rains on 30% of days. Okay, calibrated, but like not useful to tune in. So, like how does the fact that you can have this like really weak predictor and still be calibrated square with what I just claimed about decision making, that sort of the optimal policy mapping predictions to actions is the one that just trusts the forecasts if you're calibrated? Well, it's because, like in that statement, I'm limiting the policies you're considering to be policies that are only functions of the prediction itself. And so, like if my predictions are constant valued, the class of policies we're comparing to are not very interesting. They're like constant valued policies themselves, like always bring an umbrella or never bring an umbrella. And so, like if we want stronger guarantees, if we want guarantees that mean that, for example, it's a good idea for you to trust the predictions that I make, even if you're allowed to like look out the window and see that it's cloudy today, we need stronger guarantees. Okay, so multi-calibration are like a form of stronger guarantees. Here's what multi-calibration means. Let's fix like a collection of grouping functions that they're allowed to depend on external context. So it can, right? So for example, I could have the group of like cloudy days. Okay, I could have a bunch of group functions and they don't have to be disjoint, right? So I could have cloudy days and sunny days. Those are disjoint, but I could also have group functions that are defined by, like, I don't know, barometric, like pressure readings and whether it rained yesterday and whatever I like, right? I could have group functions that sub-select, different sequences of days. It doesn't matter that they sort of overlap. And we could ask, like, okay, like what is the, let's look at the distribution, not just marginally, but conditionally on each of these groupings. Let's look at the distribution of cloudy days. Let's look at the distribution of days for which it rained yesterday. Let's look at the distribution of days, for which the barometric reading was above some threshold. Okay, that's a bunch of different, distributions. And multi-calibration just asks that your predictor is simultaneously calibrated on all of these conditional distributions. So it just says, look, it's a multi-objective requirement. It's saying not only do you need to be calibrated marginally, like as averaged over all of the days, you need to be calibrated like conditional on sort of each one of these group functions being activated simultaneously for all of them. That's multi-calibration. Okay, and there's lots of reasons why multi-calibration is interesting. I'm not going to have time to talk to you about that today. Give a different talk telling you why it's interesting. Maybe just sort of, since I gave you this sort of decision making interpretation of calibration, like one thing that multi-calibration gives you is trustworthiness of the predictions, even for agents who can make decisions as a function of stuff other than your predictor, right? So if I'm calibrated marginally, but also on like cloudy days, then trusting my predictions and acting accordingly is still a best response for a decision maker who has the freedom to like look out their window and note that it's cloudy. Okay, so like the more stuff I'm multi-calibrated with respect to, the sort of more robust the trustworthiness guarantees are of my predictions. And that's sort of one example among many. It's also, like useful for this sort of interesting idea of omni-prediction, which means, I want to have like a predictor that's simultaneously useful for many different loss functions. You can recover all sorts of strengthened versions of complexity theoretic constructions with multi-calibration. It's useful for information aggregation and ensembling. An agreement you can recover, if you know what it is, a version of Oman's agreement theorem that was originally proved for sort of Bayesians exchanging true probabilities, but like actually you only need sort of simple multi-calibrated estimates. It's useful for a lot of stuff. And because it's useful for a lot of stuff, like there's an interesting question: how hard is it to actually learn multi-calibrated predictors? Like, how much data do I need? At what rates can I obtain it? Like, what is the sample complexity of multi-calibration? So that's like the question that we're asking in this research project. Okay. And there's two settings in which you can ask this question. Sort of there's sort of the easier learning setting, the sort of standard statistical learning setting in which there's a distribution and you get a training sample from the distribution and you can train a predictor. And then the question is how many how big does your training set have to be to learn a multi-calibrated predictor? And then it's also very interesting in sort of this more difficult or maybe more difficult online adversarial setting in which you have to sequentially make predictions and there is no distribution. The examples are given to you by an adversary. Okay, so like the sample complexity question in the standard distributional setting is just asking like, yeah, how big does your training set need to be to train a multi-calibrated predictor? So if I want to say the sample complexity of training an epsilon multi-calibrated predictor is at most n, what that would mean is I would need to establish an algorithm that for any distribution takes as input a training set of size n, sampled IID from this distribution, and produces a model that with high probability has multi-calibration error epsilon. Similarly, if I want to claim that the sample complexity of learning a multi-calibrated predictor to error epsilon is at least n, I need to show that there is no such algorithm. Like any algorithm that takes as input only n samples can be forced on at least some distribution to produce a predictor that has multi-calibration error higher than epsilon. Okay, and so like we'd like to pin down what is the sample complexity of multi-calibration. Sequential prediction setting is interesting. It's a maybe more difficult setting. Kind of amazing that you can do anything in the sequential prediction setting, but like there's a whole field of online learning algorithms that is devoted to this. So now you make your predictions sequentially in rounds. There is no distribution, like the examples are fed to you by some arbitrary process that could even be adversarial. At the beginning of each round, the learner observes some context. The learner then produces their prediction. Only then does the learner observe the outcome. Again, there's no distribution. All of this could be chosen by an adversary. And at the end of the interaction, there's like a transcript we've generated of the features, the predictions we made, and the labels we observed. And we can define multi-calibration error over this transcript. It's exactly what you'd think, like the transcript defines some empirical distribution. And so multi-calibration error on the transcript is just the calibration error, the multi-calibration error of your predictions on the empirical distribution defined ex post by the transcript. Okay, so again, there's kind of like the rate or the sample complexity question for multi-calibration in the online setting. So what does it mean that the sample complexity for online multi-calibration at level epsilon is at most t, well, it just means that there exists some forecasting algorithm such that, for every sufficiently small family of groups, um, and for every adaptive adversary, can promise that if it interacts with that adversary for t rounds, then with high probability the multi-calibration error is at most epsilon. And similarly, to show that the sample complexity, the online sample complexity for learning an epsilon multi-calibrated predictor is bigger than t, you just need to establish there is no such algorithm. Or equivalently, like demonstrate an adversary such that for every algorithm, if it interacts with this adversary for t rounds, will generate a sequence of predictions that have multi-calibration error greater than epsilon. Okay, so like you can these are kind of like um, sibling questions, like what's the sample complexity of multi-calibration? How many points do you need to see to learn a multi-calibrated predictor, both in like the classical statistical learning setting, and then also in this possibly more difficult sequential prediction setting. Okay, and so like the sequential setting can't be easier than the batch setting. Like kind of the statistical learning problem um, is only easier than the sequential learning problem because the adversary could just be presenting you examples drawn IID from some distribution, but they could be doing something else as well. But sometimes the online learning problem is not actually harder than the batch learning problem. In fact, often that's the case, although as we'll see, like calibration's kind of, at least marginal calibration is an exception. So you might ask, for multi-calibration, is the sequential setting problem harder than the batch setting in terms of sample complexity? Okay, so like what was known? So as I said, like in the batch setting, it's kind of easy to come up with a calibrated predictor if you just need marginal calibration. Like if I only need to be calibrated, all I need to do is predict the mean. I could, from a training set, predict the empirical mean, and so the sample complexity of calibration is kind of the same as the sample complexity of mean estimation, which means we tightly understand it. If you want to estimate a mean up to error epsilon, you need 1 over epsilon squared samples. For multi-calibration, there's like a sequence of algorithms. There's many such algorithms that have been given since 2018 that certify, a variety of like upper bounds, like some of the, I think, original algorithms, if you work out what their sample complexity is, how many samples do you need to get an epsilon multi-calibrated predictor, something really big, like 1 over epsilon to the 10th. The best algorithms that are known, we gave algorithms that have sample complexity 1 over epsilon cubed. Sort of a bit of trivia, like these are actually algorithms for the harder sequential setting, but then you can reduce those to you can reduce the batch setting to the sequential setting. A bit of trivia, by the way, like the best known algorithms here are randomized. We don't actually know how to get to these sort of 1 over epsilon cubed sample complexity bounds with deterministic algorithms. So let's see, I see there's a hand raised, but I encourage you to just shout out your question.
Hi. Yeah, I had a question about like how are you choosing the groups? Like, can the groups be chosen like adversarially, like, or are
Yeah,
you?
good. So it's a good question. So the upper bounds, and yeah, so the upper bounds basically are going to hold for any collection of groups, and in general, for finite group collections, there's in the sample complexity bound like a logarithmic dependence that I'm kind of eliding here. So like the sample complexity bounds kind of have like a log number of groups in the numerator, but they hold for like any collection of groups. And so, for example, if you want these bounds to kind of be right up to log factors, the group size can be any polynomial in 1 over epsilon. Um, for lower bounds, we're going to want to like cook up like concrete group constructions, and I'll tell you how big they are. But yeah, like the upper bounds basically are quantified over all families of groups that aren't too big, aren't super polynomial in the parameters of the problem, because the dependence is only logarithmic. The lower bounds will correspond to sort of constructing concrete families of groups that make multi-calibration hard, and the size won't be too big. But of course, like, if I don't tell you anything about the groups, like, multi-calibration could be easy. Like all of the groups could correspond to just, marginal calibration, for example. Does that answer your question?
Yeah, thanks.
Cool. Okay, so yeah, so a bit of like trivia and like a remaining open question in this area. Like the best known upper bounds are randomized. Like the best deterministic upper bounds don't get these 1 over epsilon cubed rates. And we don't know if that's like fundamental or not. It's kind of weird that you would need like randomized algorithms for like just a, batch learning problem, but there we are. Okay, so those are what's known in the batch setting. In terms of lower bounds, like like for marginal calibration, since it's just mean estimation, we sort of tightly understand the sample complexity, but there were no lower bounds beyond sort of this kind of trivial lower bound of 1 over epsilon squared that's just inherited from the marginal calibration setting and the difficulty of mean estimation. Okay. So the sequential setting, it's kind of amazing you could do anything in the sequential setting at all. It's been known since the early 90s that you can sort of, due to sort of seminal work of Foster and Vora, and if you sort of dig into these algorithms and figure out like what's the sample complexity for them, it can be made 1 over epsilon cubed. And for a long time, there were no lower bounds, again, better than kind of the trivial 1 over epsilon squared for this problem. But Mingda at UMass, together with Greg Valiant, proved the first lower bound, actually showing that online calibration is strictly harder than calibration in the distributional setting. You can't get 1 over epsilon squared sample complexity. And recently, there's been further work along this line, actually showing that, at least non-constructively, it's a non-constructive argument, you can also do better than 1 over epsilon cubed. And so the sample complexity of online marginal calibration remains open. What we know basically is that it's neither of the numbers you might have guessed. It's not 1 over epsilon squared, and it's not 1 over epsilon cubed. It's somewhere in between. For multi-calibration, we showed a few years ago how to get, like 1 over epsilon cubed upper bounds for arbitrary collections of groups that aren't too big, arbitrary collections of groups that can grow at a polynomial rate with 1 over epsilon. So like the upper bounds, depend only logarithmically on the number of groups. So kind of like the best known constructive upper bounds, like the original kinds of upper bounds by Foster and Vora, can be extended to multi-calibration. But like, again, like the only lower bounds we knew were the ones inherited from marginal calibration. Like, multi-calibration is only harder than marginal calibration, but we didn't know any specific multi-calibration lower bounds. And these non-constructive upper bounds that were given that sort of beat 1 over epsilon cubed for marginal calibration, it's not at all clear whether whether sort of similar techniques would work for multi-calibration. So for multi-calibration, we're kind of in the pre-Mingda era. Like, all we know is that 1 over epsilon cubed upper bound. We don't know any like non-trivial lower bounds except what follows from marginal calibration. Okay, and so like the theorem we sort of resolved this question. So what we show is that basically the upper bounds, the non-upper bounds are tight. So in both the sequential and batch settings, there's a group family. In fact, the upper bounds hold for group families that can be as large as an arbitrary polynomial in 1 over epsilon, but the lower bound kicks in with a group family that only needs to grow kind of like polylogarithmically with 1 over epsilon. It's like log 1 over epsilon to the cubed. And it establishes a 1 over epsilon cubed lower bound. So it establishes that together with the existing upper bounds, the sample complexity for multi-calibration in both the batch and the online setting is exactly 1 over epsilon cubed up to polylog factors. Okay, and so like a couple of things. So it says multi-calibration is actually, in terms of sample complexity, strictly harder than marginal calibration, both in the sequential and the batch settings. Like we know upper bounds that say if you only want marginal calibration, you can do better than 1 over epsilon cubed. Okay, well, turns out you can't do that for multi-calibration. So there's a separation between multi-calibration and marginal calibration. And for marginal calibration, because of Mingda's lower bound, there's a separation between the rates that you can achieve marginal calibration in the batch setting and the online setting. But an implication of this is that there's no similar separation for multi-calibration. Like 1 over epsilon cubed, you can get 1 over epsilon cubed in the online setting, and you can't get better than 1 over epsilon cubed even in the batch setting. Okay, so that's the theorem. Okay, so let me tell you a little bit about sort of what the shape of the proof of the theorem, just so that when we transition into like talking about how we sort of develop this with the help of AI, like some of those things will make sense. So like we're going to prove that 1 over epsilon cubed is the right answer. So like you should understand why 1 over epsilon cubed? Where does 1 over epsilon cubed come from in the upper bound? So let me walk you through sort of a classical upper bound, non-constructive upper bound of Sergio Hart that gets this 1 over epsilon cubed, and that'll give us some guidance about what the lower bound is going to have to do. So sequential learning, this is like a cool fact in general. It's true not just for calibration, but like any sequential learning problem. So this is a good lens also on like no regret learning. Sequential learning is just like a zero-sum game played against an adversary. Like the strategy space for the learner is the set of all algorithms mapping histories to predictions. The strategy space for the adversary is the set of all algorithms mapping histories to outcomes. The learner, like if you're going to give an algorithm with a worst case bound against an adversary, needs to go first in this game. They need to commit to an algorithm, and it needs to promise that for all adversaries, even if the adversary best responds to them, it does what it says on the box. It gets calibration at a certain rate, it gets some no regret guarantee, right, so on and so forth. Okay, so the learner has to like commit to this algorithm and promise guarantees against all adversarial strategies. So that means that, here's our learner. You can see he's like flipping a coin. He's allowed to use randomized strategies, and he's going to do things like predict a 20% chance of rain. And then the adversary, like knowing the learner's algorithm, can then decide whether it's going to rain or not. And in one place, this picture is maybe a little misleading. The adversary can make this decision as a function of the learner's state and distribution, but not as a function of their actual declaration. So we can't actually see that the learner predicted a 20% chance of rain. If the learner was randomizing, he only sees the learner's distribution over predictions. Okay. But like by the minimax theorem, since this is a zero-sum game, like the fundamental fact about zero-sum games is that the order of play doesn't matter, right? So like it seems hard to come up with an algorithm that gives guarantees even against adversaries who know what algorithm you're running and can control the universe. But like the minimax theorem like miraculously says that this is actually no harder in terms of the rates you can achieve than the seemingly much easier scenario in which the adversary is forced to go first, right? So what does it mean that the adversary is forced to go first? It means that they have to announce the distribution of rain before you need to make your prediction. Right, so like when the adversary goes first, the game seems much easier. Like like the adversary says, "Hey, guess what? It's going to rain with a 20% chance today," and then the learner can literally, with knowledge of that, decide how to make their prediction. So, for example, they can just like look at the adversary's distribution and correctly predict a 20% chance of rain. And maybe like in this order of play, it's not so surprising that the learner is able to be calibrated at a good rate. The surprising thing is the minimax theorem, that this implies that the learner can actually do just as well when they don't get to cheat and see what the distribution was. Okay, by the way, since I'm gonna like go into like showing you prompts, like here's the first one. This one's not like super interesting, but I'm going to talk about mostly OpenAI models when we get to the math, but Gemini is quite good at making like art for talks. So here was my prompt. Okay, So okay, so like where does this 1 over epsilon cubed come from? Well, think about the world in which the adversary has gone first and told you the probability of rain first. So like one thing the learner could do is report honestly. Yeah, not quite. That's actually not such a good idea, because remember, what calibration does is it sort of measures the magnitude of your empirical bias conditional on each of your predictions. So if the adversary says today there's a 50% chance of rain, and then the next day there's a 50.0001% chance of rain, and then the next day there's a 50.00002% chance of rain, if they can force you to make a different prediction every day, then there's no opportunity for cancellation. You'll have bias 0.5 every day. Your calibration error will be terrible. And so like if you want to like avoid that trap, you need to make predictions not to like arbitrary decimal precision, but at some level of like coarsening. Like I'm going to predict the chance of rain up to like 1 decimal point. Okay, so if the learner just rounds the truth to the nearest multiple of 1 over m, then on average, like they will, there's m different predictions they can make between 0 and 1. On average, they'll make each prediction a bunch of times, t over m times, and you can convince yourself having them equally spread out like that's actually the worst case. And like if I do that, when I make these predictions, I have some, just because I'm rounding, I have like bias 1 over m, and I have like some sort of noise, empirical noise in my predictions. Since I make each prediction t over m times, the noise is going to scale kind of like root m over t, and setting m optimally to trade off these sources of errors where you get 1 over epsilon cubed. Okay, but this is only like an upper bound. Like that doesn't mean that the learner doesn't have like a better strategy. You're right. So like honesty is not necessarily the best strategy. Here's like a nice example illustrating this again from one of Mingdao's papers. So suppose like what the adversary is going to do is just going to like repeat this triple. On day A, there's a 50% chance of rain. On day B, there's a 0% chance of rain. On day C, there's a 100% chance of rain. If I just report honestly, then, like I'm going to accumulate like 1 over root t calibration error because I'm predicting that, a coin flip comes up heads 50% of the time, which is right. But like if I only flip the coin t times, there's, some deviation on the order of 1 over root t. On the other hand, I can cheat. I can predict like a 50% chance of rain on day A and then see if it rains. And if it does rain, I'll also predict a 50% chance on day B, even though I know there's a 0% chance of rain. And I do this to get cancellation. So now I predicted 50% chance of rain twice, and on one day it rained, and on the other day it didn't. So my calibration error is 0. And I can just like repeat this and get 0 error. So on this particular instance, there's a better strategy than honesty. And so like more generally, if we want to prove a 1 over epsilon cubed lower bound, we need to show that there's no better strategy than honesty, even in the worst case. And one obstacle to proving this for like marginal calibration, say, is that it's not true. Like this better upper bound of Dagan et al. Shows a complicated strategy that can, even in the worst case, arrange for sort of extra cancellations. And so the intuition for what we need to do for the lower bound is that, honest prediction is a strategy that works not just for marginal calibration, but for multi-calibration. Honest prediction gets low bias on every subsequence. But marginal calibration, it's possible to kind of like overfit marginal calibration with dishonest gaming, clever gaming. And so our goal here in coming up with a lower bound instance is to find a group structure so that any kind of overfitting, dishonest prediction to one of these sequences will witness high calibration error on another one of these sequences. So it's we want to like we want to pin down the learner so that the only thing left for them is essentially honest prediction. Okay, so let me give you just like the shape of the argument. So we're going to have like an easy stochastic adversary. Every day they're going to pick like the context will just be like a number, and it's just going to like communicate the chance of rain. So like the features you see just say like 23% chance of rain, and the features are always right. Like when you see 23% chance of rain, there is a 23% chance of rain. And the adversary is going to make sure that the chance of rain is kind of like uniformly spread out on some discrete grid. So like you can predict honestly, that is a legitimate strategy here because the features telegraph to you the expectation of the label. But because the features are spread out, we kind of saw that like honest prediction is going to get you sample complexity like 1 over epsilon cubed. And if we can prove that's the best you can do, an instance like this will certify a 1 over epsilon cubed lower bound. Okay, so now we're going to like introduce some groups, and what the groups are going to look. There's not going to be too many of them, but roughly speaking, what the groups are going to look like are sort of like the indicator vectors for some orthonormal family over the feature space. So it's like some orthonormal basis. Okay. And the way the lower bound works is we show that if you want to if you have low multi-calibration error over this family of groups, the only way to do it is to make predictions that are like kind of close to honest in this L1 sense. Like if I look at the expectation over rounds of the absolute difference between your prediction and the feature, which on this instance is the true conditional mean, that has to be small. Okay, and the reason this works is because it turns out threshold functions have some low complexity representation in this Walsh basis. Okay, and then we say, okay, well, like if you're close to honest, because the features are spread out, like your predictions have to be pretty spread out too. You can't be concentrating your predictions in too many buckets. You've got to spread them out kind of similarly to what you would have had to do if you were making honest predictions. And then we say, look, calibration error, we can kind of like decompose it into the sort of noise of the predictions, like there'd be some, even if you predicted honestly, in this case, the sort of honest prediction is to just repeat back the features. Even if you predicted honestly, just for sort of empirical noise reasons, you wouldn't have zero calibration error. And bias, you're not necessarily predicting honestly. So there's also like bias, the difference between your prediction and like the honest label mean. And basically, you can show that the noise is small with a pretty complicated martingale argument, and the fact that you're close to honest means the bias term the noise is large, and because you're close to honest, the bias term is small. Okay, and you can actually, okay, this is like a whole other paper's worth of work that I don't have time to tell you about, but you can use similar ideas to prove a batch lower bound. You need a different instance because like this instance gives away the label mean in the features, and if you want a batch lower bound, you better not do that. Okay, so let me tell you a little bit about like how we used AI in this process, and maybe I'll start with some general thoughts, and then we'll go through, to the extent that we have time, like a case study for what we did in this particular paper. Okay, so like general thoughts. So first of all, I personally use OpenAI tools. In my short evaluation periods, they were like the best at math. They're very good at math. Everything's getting better all the time, though, and I haven't continued to do careful comparisons. So I'm going to tell you about OpenAI tools, but I'm not taking like a strong position that like you should use these and not Anthropic tools or whatever. At a high level, modern LLMs, I'm talking about things like ChatGPT Pro, are very good at executing on a good idea, but they're not good at starting from nothing, right? So you can't just say, prove me a multi-calibration lower bound. Similarly, like if you propose a direction that you kind of like morally understand, describe to them your intuitions and ideas, sort of, so long as those ideas are of a form where like it's really just a matter of time, like you think you understand the problem well enough that given enough time you could work it out, then in my experience the AI tools can very reliably help you execute on this with very few errors. On the other hand, you can like direct them to kind of like just blindly search through proof space, even if you don't have any ideas. I've tried this. In my experience, like it does not save time. It wastes time. They will produce very long arguments with sort of subtle, hard to find, but often fatal flaws. So these tools are very useful for sort of execution or even ideation if you have seeds of an idea, but like they're not like you can sink a lot of time into having them like try to find proofs that you don't have good ideas for, and in my experience, it doesn't work very well. Even when you get these sort of correct proofs, they're often, they feel like slop. They're poorly organized. They're more complicated than they need to be. They use weird terminology. You wouldn't want to just like, post these online without some edits. It needs like a human pass. And in my opinion, like they're not very good at exposition or intuition or organization. So like I use them on the math. I do not use them like on the introduction. I don't recommend you use them on the introduction. Some people maybe like think that it would make more sense to go the other way around because they're good at words. No, like I think these are actually very good at helping you with the math and pretty poor at writing well for people to understand. Okay, so let me tell you about my workflow. This is changing all the time. So this is, like time-stamped April 2026. So, for like an ideation brainstorming phase, I often use the ChatGPT thinking model through the web interface. I say thinking here rather than pro because for the ideation phase, you kind of want like a reasonably rapid back and forth. Like pro is really smart, but it takes like an hour, to like get back to you. It's not good for like bouncing ideas off of. Right. So these models are like think of them as like pretty smart rubber ducks that like know lots of stuff. You can talk to them. Sometimes they'll suggest connections from the literature that can point out to you why some of your ideas might not be so promising, things like that. Then for sort of proof of concept execution, what I tend to do is I tend to use ChatGPT Pro through the web interface. So I'll prompt it with like a pretty long query, usually like something like a page of text, together with maybe links to papers from literature. And what I'll say in the query is first precisely define the problem I want to solve, give intuition for why I think it's true, and what my ideas are for how to solve it. It's kind of similar to what I would write to a student or a colleague if I was trying to get them excited about an idea and, like onboard them onto like a research project, tell them what I know about it so far. Sometimes it doesn't find a plausible formalization. Other times it'll come back to you, an hour later, and it says, yeah, like, here's a sketch. I think, you can do it this way. And what I'll do in the second case is I'll ask it to produce a self-contained LaTeX document, forget the intro, to focus on precision, rigor, and correctness. Just force it to like, not hand wave and like pin down all of the details. Okay, but so here's, by the way, like the prompt that sort of I initially used when starting this project. So, like so first I, say what I'm, trying to do, prove multi-calibration lower bounds. I define exactly what the problem is. And then, actually like we started here with a construction that sort of works, like a construction for an easier case. So the construction that's being described here is for a lower bound in the easier case in which the groups which define multi-calibration can be defined not just by context, but by the predictions of the learner themselves. So this is a stronger form of multi-calibration and therefore easier to prove a lower bound for. But what we're prompting it with here is a sketch of a construction that basically works. Okay. Once you get, this LaTeX, document, I like to move away from the web interface and move into Codex. So Codex is, like a vibe coding tool. It lives on your computer, but it's not limited to code. I use it to directly edit LaTeX files in a folder that's synced with Overleaf. And it is very good for iterative refinement in a way that the web interfaces of these tools are not. So you can sort of look at your paper and you can say, hey, I think that we need to define object X in the prelims. Like we're using it in section 4, but we never define it. Okay, I can go do that. So you can say, hey, I don't think lemma 4.6 is like rigorous enough. You're skipping some steps. Like please, expand the proof. It can do that. You can say, hey, we present result A before result B, but I think it should go the other way around. It can sort of reorganize the whole paper. It can even sort of from scratch do like kind of straightforward extensions where it's big changes to the paper, but it's kind of clear how to do them. So for example, we've analyzed the results in distribution. Can you add an appendix giving like the straightforward generalization bound that comes from like a Rademacher complexity analysis? That's the kind of thing it can kind of like do in one shot. Or like, hey, like we proved a lower bound for like mean multicalibration, but it should work the same way for quantile multicalibration. Please insert this extension. Okay. Then once you have something that looks like a paper, I like to audit the proofs. So of course you need to go through the whole paper, by hand, but in parallel you can have AI agents, like go through the proof and flag issues. Pro is very good at this. It doesn't find everything, but it will find lots of stuff, and then you can do this iteratively and suggest fixes. Oftentimes, like Pro can, in addition to finding issues, suggest fixes in enough granularity that you can just kind of like feed them to Codex, and Codex will correctly implement the fixes. Okay, and then finally, you need like a final human pass. So like, I don't use AI to sort of write any of the exposition, basically, not the introduction or the proof intuition or the related work. I don't like what the AI voice sounds like, and it doesn't have the context or the big picture understanding to do a good job here. And writing a clear proof intuition for the reader, is as much for you as for like the reader. Like, of course, it's for the reader, but like you need to make sure you understand the proof if you're gonna like like write a paper containing it. And being able to write like a clear proof intuition is a good check to make sure you do understand the proof. And finally, there's this phase that I think of that I've been calling deslopping. So basically, even when you reach a stage where sort of the proofs are technically correct, like AI proofs are like weird. Like they use weird terminology. They sometimes they really like measure theory. They use, excess formality in places where it's not needed. They'll invoke measure theory even when you have, like finite constructions. They're much less modular than they could be. Oftentimes, a good organizational pass will make them much shorter. So you need to like deslop the exposition. Okay. We're almost at the hour. What I have slides basically going through like a case study of the history of like these papers specifically, and there's all sorts of twists and turns. But maybe I'll pause and ask what we want to do now. I'm happy to either like go through this case study or I can kind of like, go through my conclusions and we can move to Q&A and, it's fine if some of the questions are like, can you tell us about the case study?
Yes.
So do people have a preference for what we should do now?
I mean, it would be great if we could go through the remaining materials there, but how about just pausing a little bit to see if people have some questions right now, and then we can jump to the next part. I mean, we have time, so, and I think that the student part is gonna be also flexible, but let's see whether there are some questions. I think some people may want to drop at 2. So if there are questions, maybe we can just move forward with them and then switch to this part.
Okay, cool. Yeah, why don't I pause for questions then?
Good. Just go ahead and ask questions, Elliot.
Thank you. I'm concerned, as someone who sometimes works with interactive theorem provers and all to get really totally sound proofs, we would hope anyway. To what extent I should trust this whole process? How much can I trust the math coming out of the tool? How much can I even trust the checker?
Yeah,
and how can we improve that situation?
Yeah, so that's a great question. So, just as with purely human written papers, like it depends on the author. Um, in general, like these tools are pretty good, but the error rate like per lemma is high enough that like if you just tried to like write a whole paper by asking it to like keep going and not check anything it did, it would quickly like go off the rails and start like once an error is sort of once it introduces some error, these tools are sort of very happy to continue propagating that error. And so it is very possible, it's very easy to write a paper with these tools that you should not trust. Now, I think it's also not that hard to write a paper that you should trust, at least as much as, like a classically written paper. Like to use these tools to write a good paper, you need to make sure that you're not letting the tools lure you outside of your expertise, which is very tempting, by the way. But like, it, the success rate is high enough, at like the lemma level that if you understand roughly what's going on, it is possible to kind of catch errors as they are introduced. And like one thing that's a little interesting, it's an interesting phenomena. Like take a sort of traditionally written paper from Stock or Fox before the AI era, entirely human written. It will be riddled with errors. Like, take any given lemma and like probably the lemma is like not quite true. Like, there might be a sign error somewhere, like, the constants might be wrong. But like empirically, by and large, it doesn't matter. Like, empirically, like, usually the sort of theorems are kind of like morally true, meaning there is a way to fix the errors that does not meaningfully change the result. That why is that? Well, I think it's probably because like the papers that we see are not sort of the result of some like just blind search through proof space, but are kind of like the projection from some, like higher level human understanding into like an attempt at like a formal communication of why the result is true. Now, if you just have like AI models, like you can have AI models kind of like blindly search through proof space, and the proofs they produce do not have these properties. Like, like the sign error on page 18 can be like the thing the whole thing hinges on. Um, and like why this difference? Again, probably it's because what we're seeing is really like the thought process, and an error is, could derail the whole thing. So anyways, this is all to say that it's important when using these tools to make sure that you understand at an intuitive level what is going on and that you're not being led through some, blind search through proof space. Um, Ultimately, of course, like all responsibility lies with the author, and we should not trust things unless we ourselves understand them.
Right. So it remains up to program committees and reviewers to try to judge the level of responsibility of the authors.
That's right. One other like interesting thing I'll note that program committees are going to have to figure out how to deal with, until we get to formal verification. Like these AI models are like seemingly pretty good at informal verification. You can like feed them in a paper, and ChatGPT Pro can like think for a while, and it can oftentimes, if there are errors in the argument, like surface them. But like you can come up with adversarial examples for these models, right? So if you take like a human written paper, ChatGPT Pro will do a very good job of finding errors. But it's also possible to kind of just like run these things on a loop where you say, okay, try to prove this, and then you say, okay, find an error, and then if it finds an error, you say fix it. And you can run these loops and reach a fixed point where the models don't find errors, but the arguments are still fatally flawed. Um, so like for the distribution of like human written papers, they're actually pretty good at finding errors, but like we're going to start to see adversarially generated kinds of papers for which these models are not reliable verifiers, and we're going to have to figure out how to deal with that.
Good. Okay, so can I also ask a quick questions. I mean, I'm sort of trying to map whatever, like David 2 days ago was talking about the way that their workflow was running using AI in their workflow and what you have been describing here. Uh,
Hmm.
a big difference that I notice is that I mean, perhaps Google research at large, I would say, they emphasize a lot on the role of this agentic workflow that, like there are agents that they just try to iterate over and try to make the arguments stronger, similar to what you just mentioned right now. And they reported some numbers and results that like for example for IMO problems like the model that it's out of interactions between agents that somehow some of them is problem solver or idea generator or the other one is a verifier or trying to find the bugs and other things. There has been substantial sort of improvement in terms of the results. I was wondering if you have used this type of agentic interactions between having AI agents taking different roles in your personal experience in this space, and if you see any difference.
A little bit. So let's see. So one thing I'll say is like a lot of the focus of like AI for math that's gotten the attention, especially at big tech companies, have been kind of like trying to use these tools to, like autonomously solve hard problems. Like let's solve some like Erdish problems or some cult open problems. And that's cool, but like that's never been the kind of like research I do, and I don't think it's like that's not the kind of research that most like theoretical computer scientists do. You don't just like take a pile of like open problems and like take the first one off the top and try to solve it. If you can do that, that's great. Um, but like what I've been using these tools for is sort of a different kind of research where I'm sort of simultaneously trying to like figure out like, what are the right questions to ask and what are the answers to those questions. And you kind of like do that, in some, iterative EM style way. Like if you can't answer the question, you ask a different question. Um, and here, like, in my experience trying to automate this, I don't have the, as sophisticated tooling as they do inside Google, I'm sure, but trying to a little bit get agents to do this kind of thing. There's this gap where like these models are getting very good at algebra, but in my, biased view, like they don't have very good taste. They can produce true theorems, but like there's lots of true theorems and they don't tend to like gravitate towards the true theorems that are interesting.
Mhm,
And
mhm,
so,
mhm.
you know, today, as of 2026, I like to believe that, my like advisory wisdom still has like a little bit of value added. Maybe in 2027 that's no longer going to be true, but like you can kind of like try to throw proof search tools at problems if you'd already know exactly the problem you want to solve because it's, like an IMO problem or an Erdish problem. Um, but as soon as like the task involves not just solving exactly the problem in front of you, but like maybe iterating through problem space to find an interesting problem you can solve, I think that these tools are not yet good enough
Mhm.
to do this kind of thing autonomously.
Good, good, perfect. Thank you. Any other questions? It's 2:07. Uh, how about just moving forward with the last part, hopefully quickly, and then hand it over to Adam for the last 10, 15 minutes for the
Okay, cool.
session.
Yeah, and I am, if there's more
Let's go.
questions, I'm happy to stay on longer. So let me just go through like a quick like um what I'll
So
call.
you are comfortable to this part to be recorded to still within
Yeah,
the
yeah, that's fine. That's fine. So let me go through like poorly remembered and also poorly documented history that I tried to like reproduce for the purposes of this talk, but I have forgotten important parts of it. Um, so the history of these papers. Um, so the first time actually so I was like kind of busy at Cult 2024. I was the chair. But there was like a little bit of time, and I was having these interesting hallway discussions with my student Natalie, and we were talking about multi-calibration lower bounds. And this was before any of us were using AI for research or maybe someone was doing it, but like me and Natalie weren't. And we sort of over the course of a few days, like hanging around at Colt, we kind of came up with a verbal description of a t to the 2/3, 1 over epsilon cubed multi-calibration lower bound, but not in the full generality that I presented to you today, but in sort of the simpler, easier setting in which groups can depend not just on the features, but on the predictions. So it's still an interesting lower bound, but it's an easier lower bound to prove because the groups have more power. And we got to the point where it kind of like seemed doable, like, but it wasn't clear on its own how interesting it was, and it seemed like it would require some messy martingale arguments that would take a lot of work, and so we kind of like forgot about it. So that was summer 2024. And then through some happenstances, like time passed, and it's like almost winter 2025, and now we've got AI, and we kind of remember the problem, and I prompt ChatGPT Pro with sort of like a poorly remembered version of like this construction we'd been talking about at Cult, and I kind of misremembered it, like I didn't quite define things right, and ChatGPT is able to point out problems with the construction, but after some amount of iteration, it's able to agree on a construction. It can kind of produce a complete proof. And this is, by the way, like now the first sort of like the warm-up result in our paper. Okay, so there's a lot of stuff truncated here. If you use ChatGPT, it gives you like pages and pages. So this is heavily truncated. But just kind of to look at the shape of the conversation, I gave it like this construction. It's like, yeah, like I think something like this can be like made to work, but there's like a problem. I sort of say, well, there's something in your proposed solution that doesn't make sense. It's like, oh, good point. You're right to be suspicious about that. Like, here's an idea. I say, does this help? It says, it seems like it might help, but like it doesn't. And we go through like that. I give it another idea. It's like, yeah, like great idea. That helps a lot. And then I finally, the whole thing sounds plausible. So I'm like, all right, like let's see if this really works. Like, let's, write this up as a self-contained LaTeX document. Don't skip any details. And it does. And, we need to like deslop it, and it goes through the whole process I've talked about. But like, by and large, it produced here a correct proof. Okay. So, that's kind of the warm-up result, though, because really we want to prove a result about like multi-calibration as it's like classically defined, where the groups depend only on context. Okay, so we've got some ideas. So we've cleaned up substantially, filled out the details. We use Codex for this. The sort of warm-up result, which is now a cleaned up LaTeX document, fleshed out, pseudo paper. I upload that to ChatGPT Pro, and I've got some ideas for how you might extend this to like a lower bound for the prediction independent case. And basically like ChatGPT tells me that my ideas are stupid and says nothing can work. So here's the prompt, so I'm like, all right, here's the document. I attach it in the prompt as LaTeX. It's better at reading LaTeX directly than trying to parse PDFs. And I say, we want to extend it in this way. Here's some intuition. Here's an idea. And it comes back and it says, your idea is stupid. Like, here are the reasons. And I interact with it for a bit, and it's like, look, dude, let me level with you. Like, I don't think it's going to work at all. I think like this whole thing is like impossible. But okay, like I iterate. I basically spent 2 weeks like doing this like pretty intensively. And like it wasn't impossible. So I go back and forth. Here's what the back and forth kind of looks like. I'm like, I don't buy that it's impossible. Like, here's some ideas. it's like, those ideas don't quite work. I say, like, here's some notes. Like, I think, something can be made to work. Let's think about it more. And finally, like after 2 weeks of this kind of interaction, it proposes like something that resembles what turns out to be like the group structure in our actual lower bound. Okay. And so I'm like, great, like let's try this thing again, where I ask you to produce like a proof in LaTeX, work through all the details. And it does, and it gives me one, and I celebrate. And I have like a really good weekend where I'm happy that we got this proof. But then I read through it, and like there's like a pretty serious error. Like there's like a key step that just is like wrong. And so, I go back to ChatGPT Pro, and I'm like, dude, like, there's this serious error. I attach the draft of the thing it wrote, and I point out what the error is. Okay, so we iterate, and it figures out a way to, or it gives an idea for how to fix the error with basically a complicated martingale argument. There were a number of false starts. So like GPT does this thing where it knows like a lot. So it like recalled some like really useful martingale theorems that I hadn't known about, but like it like conveniently forgot about some like technical preconditions that made them not really apply. And you don't really like, so you shouldn't like trust the theorems it gives you. You should like look up the papers they come from and like check that all of the conditions are actually there. So there was some iteration where I did that, and I was like, you're not using the theorem correctly. Okay, but fortunately, like my student George is very smart, and he knows enough about martingale arguments, and he's able to actually turn this into like a rigorous proof. Okay, and so like we go through this codex process of expansion and iteration and proof checking and cleanup, and finally we get like a rigorous lower bound that isn't as strong as what we now have. Instead of a 1 over epsilon cubed lower bound, it's like a 1 over epsilon to the 5 halves lower bound. And it's because this connection between multicalibration and approximate truthfulness existed only in like a weaker form. And I knew that we wanted to aim for the 1 over epsilon cubed lower bound. So of course, like I asked ChatGPT, like, hey, do you have any ideas for how to like improve this? But it didn't really, and neither did I. And so, me and ChatGPT were kind of stuck, but there's still some like team human. So Joe and George, they could sort of take this correct argument proving a weaker lower bound and kind of see through how to extend it to the tight lower bound. Okay, and then we go through like a top to bottom like deslopping. We like digest the proof, we explain its intuition, we reorganize the whole paper. It's completely deslopped. We post it online, and we've got this open question. We're like, hey, we've got this tight lower bound, but like it has a big group family. The size of the group family is polynomial in 1 over epsilon. Like maybe there's a construction that has, like an exponentially smaller group family. In fact, in our archive paper, that is like the open question that we list at the end. And so, like we were thinking about this. Of course, we'd ask ChatGPT Pro for ideas, nothing. But then in March, like 5 days before the conference deadline, actually I'm traveling. I'm like in Atlanta at some event. Joe like sends like a Slack message. He's got like an idea how to do it. Like awesome. He can like thinks maybe he can solve the open problem. But we're like 5 days before the deadline. But like together with ChatGPT Pro, he can like flesh this out into like into a complete proof. But like even so, we have like a fully written paper. Like the thing is like 60 pages long, and we need to like thread this new argument. It's going to change what all the results are. We have to like change all sorts of stuff. But given the like, but basically once we have Joe's idea, like this is just sort of mechanical work essentially to thread everything through. It doesn't require like any new like feats of genius. And this is the thing that Codex is really good at. So we're able to update the paper in about a day. Okay, so just now these are like screenshots from Codex. I'm like, hey, the codex session's already, we've been working on the paper, so it's already very familiar with like our paper. I put a new file in there. I'm like, hey, here's like a new file containing this improved proof. Like, what do you think? It says, cool, it looks like a good proof. I ask it to do a line by line proof audit. It finds a couple of issues, but nothing major. And I say, okay, like fix the issues you found, and then let's make a plan to propagate the argument through the rest of the paper. And it does. And then I say, okay, let's execute your plan. And it does it. Again, like there's no new math in this. This is all sort of like the math is proven, but it needs to be like threaded through the paper. And it does this. It sort of makes edits across the whole paper. Okay. Yeah, and that's kind of the story of the paper. So anyways, just to the final musings, and then we'll like go to questions. So like execution of well-formed ideas has become much easier. It's become much cheaper. Like ChatGPT is not yet at the place, I don't think, where it can reliably have good ideas for you. But if you have a good idea, like it can really make execution easier and faster. And so this means that like good, interesting, creative ideas are going to become relatively more valuable than they were before. And sort of skill about technical wizardry, skill at sort of proving difficult things, doing algebra, is going to become relatively less valuable because that's what the tools are good at the moment. They are still not good at sort of coming up with proofs if you don't have any intuition or good ideas. Like you can use them in that way. You can have them orchestrate long proof searches. I did this as an experiment for something I wanted to prove. I didn't know how to prove it, so I kind of had like Codex running a loop for 2 weeks. And like at the end of 2 weeks, it was like, hey, I've got a solution. It gives me like 60-page tech document. And you look at this thing and it's like not clear whether it's right or wrong. There's no intuition, but like you like start reading it and line by line everything looks right. But it turned out there was a sign error on page 18, and like as I was saying earlier, like if you find an error like that in something human written, it's often no big deal. You can fix it. But in this case, like everything hinged on that sign error. Like it got to that sign error and then it continued. And so like these tools are not especially useful for like blind search through proof space. It's now very easy to quickly explore ideas. So one thing I find myself doing is like quite frequently I'll have some idea. I don't know if it's any good or not. Previously, like I'd have to, it was only occasionally would I spend the time to actually kind of like pull on a thread and see whether it goes anywhere. But now you can jot down a few paragraphs and ask ChatGPT Pro to flesh them out a little bit. And you can sort of much more quickly see whether there might be something interesting there or not. Usually the answer is no, but it's like cheap to check. And as I was saying, like models do not yet have what I would view as good taste. They're very happy to like lead you down rabbit holes of writing very long, very boring papers that might even contain true theorems, but are not interesting. And they're this powerful force multiplier in like your area of expertise, but like because they can take you down these rabbit holes, it's kind of important to stay within your area of expertise. It's really tempting to let them lure you outside of your area of expertise. And they try all the time. They're like, oh, I think I know how to prove this using this thing you've never heard of. But in my experience, when you go down those rabbit holes, you can like waste weeks and get nowhere. And one thing I think we all need to figure out is, like how are we going to train students in the presence of these tools? So because the tools are like not really reliable enough to produce good results outside of your area of expertise, you should think of them as like force multipliers for people who already have expertise and intuition and experience. And I like to think I have those things. But how did I get those things? Well, it was because like when I was a PhD student, I like had to like sweat through, proving lots of theorems that probably like my advisor already knew how to prove at a high level, but like having me do it was a good way to train me. Like the models are very good at that, but like we have to be careful not to like replace, like training exercises. And with that, let me end. Let's see if anyone wants to chat.
Thank you